Well, we talked about MATLAB itself and getting it started, and then starting off with MATLAB calculations, and we saw how to do basic arithmetic calculations with MATLAB. And we are now here, matrix algebra. The fundamental object in MATLAB is a matrix that can be zero-dimensional, which is just a constant, one-dimensional, a vector, a list, two-dimensional than what you normally know as a matrix, and a higher dimensional object, which I'll talk about just now. In MATLAB, you construct a matrix, so we call it A, give it a name. So you want a 2x3 matrix. You start off with the square brackets, and you indicate the end of a row with a semicolon. So here we've generated a 2x3 matrix called A, using the square brackets to tell MATLAB we're making a matrix, and the end of each row is indicated by a semicolon. And the operations on matrices are as you'd expect: multiplication, addition, subtraction of matrices. That's the transpose, and there are some others which we'll talk about just now. Well, here's our matrix A. Let's form a matrix B by multiplying the matrix A by 2. This is scalar multiplication, and it's a pointwise operation, an element-wise operation. It is scaled up all of the elements in A by 2. Let's form a matrix C by taking A plus B, and it's added the elements of A to the elements of B. That's matrix addition in the traditional form. It's a pointwise operation or an element-wise operation. Here, C1 is formed by adding 1 to the matrix C. And although these are not compatible for matrix addition, because this is a scalar and this is a 2x3 matrix, MATLAB does the most reasonable thing, and it adds 1 to every one of the elements in C. So it takes these elements and adds 1 to each one of them. So it's a pointwise operation of addition. And here, if we got the matrix A and add the column 1, 2, that's a column, because the first row is 1, and that indicates the end of that row, and the second row has just got a 2 in it. So this is a 2x3, and this is a 2x1. So you can't add them with traditional matrix addition, but MATLAB understands what you mean. Add this column to all the columns of A. So you take this matrix A here, and you add the column 1, 2 to it. Add column 1, 2 to that, and you get 2, 4. Add column 1, 2 to that, and you get 7, 6. Subtraction, indicated by the normal symbol, and transpose. Here we've got the matrix D, which is 2x3, and the transpose is indicated, the little dash here, and this is then a 3x2. This is the symbol which is used to indicate matrix multiplication. So let's give ourselves this matrix, which I'm calling little x, which is a 2x2, and y here, which is a 2x3. And we multiply them to form the matrix Z. This is matrix multiplication. So you take row 1, 2 times column 5, 8, that dot product, the normal matrix multiplication. So it's row 1, column 1 gives you the element here in position 1, 1 of the product. Of course, the matrices have got to be compatible. So if you take our previous matrices and try and multiply them, MATLAB will complain, there's an error, they're not compatible for matrix multiplication. Now, if M is a square matrix, then it's compatible with itself for matrix multiplication. So, for example, if this is our matrix M, we can cube it. That means multiply M by itself 3 times. And so the matrix multiplication can be achieved. We've also got the pointwise operations, and then it is indicated with this little point here. So, for example, if here is M, the pointwise square of M is that matrix which is obtained by taking the square of all of the elements in M. So if we have a matrix M and N, there's the matrix N, there's the matrix M, we can form the pointwise product of the two. That is, it multiplies them point by point, element by element. 1 times 1, 2 times 4, 3 times 9, and 4 times 16. The pointwise product. If this is a vector X, a 1 by 7 list, a matrix, a vector, then we can take 2 to the pointwise power of X. So it'll take 2 and multiplied by all the powers in X, the pointwise power of X. Now, the usual precedents of the arithmetic operations are respected by MATLAB, and you can always override those by using brackets. So here, if I call a 2 cubed plus 2 times 4, then that is done first, 2 times 4. 2 is cubed up, and then it's added. Of course, addition is commutative, so I could have done this first and then added that. But the point is that this operation precedes the addition. The cubing precedes, and then we add afterwards. Now you can change that order by using brackets. So for example, if we want to take 2 to the power 3 plus 2, so instead of this here, we bracket the 3 plus 2. The bracket is applied first. 3 plus 2 is 5, 2 to the 5 first, and then you multiply by 4, and so on. So if there's any possibility of confusion, use brackets to indicate the order in which these operations are performed. MATLAB has got many built-in functions, and you can, of course, make your own functions, which we will be doing. But all of these functions in MATLAB operate on matrices. So if you make a matrix A, take the sign of A, it takes the sign of all of the elements in A. If you go to the help window, you can look at all the functions available. But this is part of what you will see if you go to the help center. It'll take you through all of what's available, and you can see all of the built-in functions and everything else. If you don't want to go to the help window, you can just type help and whatever you're looking for. So elementary functions are obtained by typing help L-fun. Here are some of the functions which are then produced when you type L-fun, help elementary functions. It'll bring up these and many more. MATLAB has the arithmetic functions, which take the floor and the ceiling, fix and round, and so on. Just to illustrate, say we give ourselves a matrix M, and we fix M. Then it rounds towards 0. So this 2.5 here, it rounds towards 0, so it'll go down to 2. If you look at, say, minus 2.5, it'll now round towards 0, up to minus 2. The normal rounding operation rounds up to or down to the nearest integer. So here we give ourselves this matrix, and we round it. It'll round to the nearest integer, and if you add the extra information, round to correct to n decimal places, it'll do that for you. So if here is an M, and now we see all the places which are exhibited, format long, round it to 3 places, it finds the nearest floating point number, which is a constant which we'll talk about just now, correct to 3 decimal places. If we give ourselves this matrix M again, then formatting short, it rounds to 4 decimal places, and you can round it to 5 places if you like. So this shows that these are the closest floating point numbers to these ones in here. It is really formatting long will show you all of them to 15 places. Formatting short is 4 decimal places. Formatting bank is 2 places, and there's hardly ever going to be any real reason to round to, say, 7 decimal places. So just bear that in mind. Formatting long if you want to look at what is going on further down the line in some calculations, say convergence of a sequence. Formatting short will be the format that you will use mostly, and sometimes for financial calculations you'll need format bank. The arithmetic operations taking the floor and the ceiling. Say we take this matrix M, take the floor. It rounds towards minus infinity. In other words, it finds the next integer down towards minus infinity to the left. So over here, 3.14 rounds down to 3. Minus 3 and a bit rounds down to minus 4. And ceiling does the opposite. You should experiment on your own with these. We generate lists in MATLAB with this syntax. So you tell it the list M, which is a one-dimensional vector, is going to start at 3 and go in jumps of 2 until you get to 11. And it'll do just that. Start with 3, jump by 2, jump by 2, jump by 2, jump by 2. If now you tell it the same command over here, but you tell it up to 10, it'll do the most reasonable thing. It'll go as far as it can. So it gets up to 9 over here. The next jump would be to 11, but you told it to stop at 10, so it will stop at 9. These jump sizes, they don't have to be integers, of course, and the starting and end points don't have to be integers. So here you're telling it to start at 5 and going a jump of minus 0.5. So 5 minus 0.5, 4.5. Minus 0.5, 4, and so on. Normally, or let's say the default increment is 1. So if you don't specify this in between jumping size, it'll assume it's 1. So you tell it X is a list starting at 3 and ending at 7, then it'll take it that the jump size is 1. So it'll go from 3 to 7. Lists can also be generated with the function linspace. So you can tell it then in this syntax, you're making a list from 0 to 1 and you're specifying the number of elements in the list. So we're going from 0 to 1 and there must be a total of 5 elements. So it's sometimes a more convenient way of generating lists. So experiment with this on your own. Try these out and see how it works and compare the two. There's some standard matrices in MATLAB. I for identity, that's quite cute. I3 means the 3 by 3 identity matrix. It'll generate a matrix of zeros for you, and you specify the size here. Ones, it'll generate a matrix of ones, and it'll make a diagonal matrix for you. You specify the diagonal elements, and it'll make a matrix of the appropriate size with those numbers down the diagonal. There's a slight variation on this. If you tell it to offset by 1, then those elements are shifted 1 to the right. As another example, say you give it the diagonal elements, a 1 by 3 matrix with 2's in it, and then you tell it to shift 3. So it'll make this matrix and it'll put the 2's down the diagonal, but it has shifted 3. So it makes the matrix of the appropriate size. You can find the size of any matrix using the function size. So size of A will produce the number of rows and the number of columns in a vector. MATLAB has got its own random number generator, and you can type help rand to see the details of that. If you tell it rand3, it'll generate a 3 by 3 matrix, and the elements in the matrix will all be uniformly distributed in the interval 0, 1. If you specify the size of the matrix 2, 3, same story, but now it generates a 2 by 3 matrix with elements in the interval 0, 1. You can scale them up. So if you wanted them not in the interval 0 to 1, but 0 to 100, you just scale it up. If we wanted integers in the matrix, we can generate the matrix, a 2 by 5 matrix, with numbers in the interval 0, 1, and then scale them up by 100, and then take the floor, and that'll give us integers. There's another way of doing this, which I'll talk about just now. We can translate as well. Say we give ourselves a 2 by 5 matrix with numbers in the interval 0 to 1, then we can translate back by minus 0.5. Now they are in the interval minus 0.5 to 5. And so on. We can use arithmetic operations to get matrices of any size that we specify and with numbers in any range that we want. We'll make our own function to facilitate this process, and MATLAB has also got an extension of this simple rand function. This function rand_i is very useful. We make our own, but MATLAB has got this one, and it generates lists, and it'll generate higher dimensional objects as well, which we'll talk about just now. And you can specify the range, but rand_i generates integers. Have a look at the help file for that, and for example, here, rand_i gives you you specify the size, a 2 by 3 matrix, and the numbers that occur there, that tells it it's got to be between 1 and 10. Of course, we can modify the rand function to do that, and we will do that ourselves, but this is the built-in MATLAB function that does that. If we've got a matrix A, for example, and we want to extract the element in row I, column J, then you do that with the syntax A round brackets ij. So if that is our matrix A here, A24 is that element in row 2, column 4. Row 2, column 4, and it'll extract the element 8. If you now don't say Aij, but A colon J, that means all of the rows, column J. So in this particular example here, A colon 2 means all the rows, second column. It will take all of the rows, second column. All of the rows, second column. If this is our matrix A, and we want to extract row 3, we do this. We tell it, row 3, all of the columns. So that colon there means all of the columns. So it goes down to row 3 and then goes along all of the columns. There's an extension of this, then you can give it a list. So if I and J here are lists, and you tell it A, all of the elements in I, all of the elements in this J, say for example A 2, 3, 4, then you're extracting all of the elements in rows 2, 3, 4, and columns 4, 6. So it'll extract them out of this matrix. Let's give ourselves that matrix again, and we now, instead of A fixed I and then colon, which extracts ith row, or if we say A colon J, that'll give you the jth column. A colon lists all of the elements, and it does it in this way. It goes down column 1, puts it there, then down column 2 and puts it underneath it, down column 3 and puts it underneath. So it always makes a column. A colon makes a column out of all of the elements in M formed in that way. down this column, down that column, down the next column. It works its way through the columns of the matrix, making a column vector. So you always get a column vector coming out, and this will turn out to be very useful. Now, by default, MATLAB operates down columns. So if we've got a matrix M, and I tell it to extract Mn, it'll make a column out of M using M colon, and then extract the nth element. So the way it operates is to effectively to go down column 1, down column 2, until it hits the 4th element, if we're asking for M4. So it goes, if we're looking for M4, goes down column 1, down column 2, and there's the 4th element. It's the 4th element in the column matrix, column vector that it would make. If we wanted to find M5, then it goes down column 1, down column 2, until it hits the 3 here in the 5th position. So Mn is the nth element in the column vector that it makes from the matrix M. So as I mentioned, as a general rule, MATLAB operates down columns. That's what it considers to be the first dimension. So if we give ourselves a matrix, the MATLAB function max operates down the columns. So max of A is not the maximum element in the whole of the matrix A. MATLAB goes down each column, picking out the maximum in each column. So it returns a vector, a list, with the maxima of each column in that list. It's got an extension of that function. If you tell it now VI, in other words, you give it an output of the max function with two components. V is the value and I is the index. So working down this column here, it picks out the maximum value, V, 98 in this case, and its position in this column was 1. Looking down the second column, picks out the maximum, which is 89, and it records its index. It was the 4th element in that column. If you want the max of the whole matrix, then you've got to form the max of A, then that gives you all the maxima. Then you take the max of that, which will be 99 in this case. There's also a min function which does the same thing, and the product function. If we give ourselves this matrix and you ask MATLAB to form the product of A, it doesn't multiply them all. It works down the columns. So it takes product, 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 going down the columns, and here we are. That's the product of the elements in the first column. This is the product of the element in the second column, product of the elements in the third column, and so on. Similarly, if we give ourselves a matrix A, the sum function works in the same way. It takes the sum of the elements in that column, the sum of the elements in that column, and so on. It doesn't sum all of the elements in the matrix. If you wanted the sum of all of the elements in this matrix, you have to take the sum of the sum. The MATLAB also has a cumulative sum function. So if we give ourselves a matrix, it takes the cumulative sum of these elements as it goes. So the cumulative sum here is 10, and then 10 plus 6, 16, and 10 plus 6 plus 6, and so on. Works down matrices as well. It takes the cumulative sum as you go down here. So 3, and then 3 plus 3, and then 3 plus 3 plus 2, and so on. Working column-wise as usual. Works down the columns, taking the cumulative sum as it goes. MATLAB has also got the facility to make dot products. So you give it two lists of compatible size, take the dot product of the two, and it'll also take the cross product of three-dimensional vectors. And you should experiment with these. It's also got very useful set functions. It'll take the difference the set difference and the union of sets specified by lists. So I've got a 2 by 2 matrix and I want to make a new matrix, which is a 4 by 2 matrix. And in the first block, I want the old matrix, and underneath it, I want a multiple of this one, say twice that. I do it like this. I tell MATLAB, make a new matrix, also called M, and in the first block you have M, and underneath it you have 2M. Then there it'll make that matrix for you. M is here, 2M is here, and that's your new matrix formed from the old. We'll call this augmenting. You're augmenting this matrix by putting a matrix underneath it. Similarly, if that's our matrix, and I tell it make a new matrix called B now, and I want A in the first block, and I don't put a semicolon here, I just leave a space or a comma, and it'll put A in the next block to the right. So it'll form a new matrix B with the old matrix A in the first block, and in the second block it'll have the matrix A, or any multiple of A, or anything to do with A. Similarly, if I tell it now make a matrix B, takes the old matrix B, puts it here, and then puts 3B underneath it. The semicolon says put the next one underneath it. MATLAB also can allow you to make empty matrices. So you start off with the matrix E, and you put the matrix square brackets here with nothing in it, so it makes the empty matrix. This is sometimes useful when you want to start off a procedure, make an empty matrix, and then keep putting things into that matrix and augmenting it as you go. So here's an application. We've got a little problem. We've got a population starts at 1,000. We look at it increases at 5%, and at the same time it's then culled at the end of each period. Then there are many ways of doing this, but one way is to start with an empty matrix, put things into it, and then keep augmenting as we go. Now here's one way of proceeding with that problem. Not necessarily the best way, it's just a way of doing things. We make an empty matrix. We specify that the year starts off at 0 and the initial population P is 1,000. And we put those into that empty matrix. Of course, we could have started with this matrix, but sometimes it's nice to have a fixed way of proceeding. So we make an empty matrix and we put these two values, the year and the population, into the empty matrix to initiate it. So we calculate the new values. The new value of the population increases by 5%, subtract 10 for culling, and increase the year by 1. Then we augment V. So we're making a new vector, which we're also calling V, from the old vector. So that was a row, and now we put a new row underneath it, indicated by the semicolon. So there's the initial V, and there we've augmented the initial V by this row. And that gives us then the year and the population in that year. And we continue like this. The new population is the old population times 1.05 minus 10. Increment the year, and then augment the old V. Again, calling it still V. So a new V is this augmented vector with the old V in it. Now that old V is a 2 by 2, and we put a new row into it underneath it. So we've augmented the old V with this new row. And we carry on like this, increment the year, increment the population, and then augment. So the new V is the old V with a new row underneath it, and there it is. And MATLAB has now switched automatically to exponential format, scientific notation. So here this is all multiplied by 10 to the power 3. It's all multiplied by 1,000. If you don't like that format, we can get away with using another format, but MATLAB will switch when it is convenient. There are many other ways of doing this, but here it might be a more convenient way. We specify then V11. So we're making an object V. We don't have to tell MATLAB what it is. We just tell it that in position 1, 1, there's a 0, and in position 1, 2, there is 1,000. So it'll automatically make a 1 by 2 matrix, a row. Then we work going down the rows. So in position 2, 1, we increment the year. These are the years. We increment by 1, and you see it's now got a 0 by default there. And then we do the calculation to find the new population. It's the value in 1, 2, in row 1, column 2, multiplied by 1.05, increase by 5%, and subtract the 10. And then that 0 will become the new value here. And then we carry on like this. Look at the third row. So this is the third year. Well, from the start, so 0, 1, 2. And then we do the same thing for the population. You take the old population times 1.05, subtract 10, and we get the new population. You can reshape matrices. For example, let's give ourselves this matrix here, 4 by 8, so there's 32 elements in it. I can reshape that to be an 8 by 4 if I like. And it'll do the most reasonable thing. See how it has done it. It's taken this first column over here, and there it appears again. And the second column, 6 down to 42, appears here. And then it'll start over here, 30 down to 77. And then the next column appears here. So it's working down the columns, reshaping the matrix. Of course, the new one, the size of the new one, must have the same number of elements as in the old one. You can replicate matrices. Say we give ourselves this matrix here, which is 2 by 3. C is a new matrix we're making by replicating the old matrix B 3 by 4 times. So it makes now what we could call a block matrix. There's 3 by 4 in this new matrix, but each of the B's is itself a matrix. So it replicates this matrix 3 by 4 times. MATLAB's got a sorting function, and you can type help sort to see the details of that. But say we give ourselves this matrix and we ask it to sort. It'll go down the columns. So it'll sort, and by default, it'll sort into ascending order. So it'll take this column here and sort it into ascending order to get this column. Sort this column into ascending order to get this column, and so on. If you wanted to sort in descending order, then you can specify here. Give it a text command, and it'll sort it in descending order. So they're going down now. And MATLAB by default takes column-wise as the first dimension. If you tell it sort M second dimension, then it'll sort along the rows. So it'll take the original matrix and then sort the rows in ascending order. Now the sorting function can also have an output, a two-dimensional output. Say we start with our M as before, and we ask it now to produce a matrix, which I'm calling MS, to be sorted M, and an index matrix I. This is what happens. We make our matrix M, then we ask it to sort it, producing a sorted matrix MS and an index. Now, by default, it'll sort down the columns, and it'll sort in ascending order. So this first column becomes 5, 11, 20. So it's sorted that. And this one tells you the index in the original matrix. So here, this 5 was in position 3. The 11 was in position 1, and so on. So it produces two matrices, the sorted matrix and the index, telling you where they were in the original matrix. You can manipulate matrices in many ways. It's got these commands which will flip the matrix upside down, flip from left to right and rotate by 90 degrees. Try those out. Give yourself a matrix and see what happens when you apply these commands to change the matrix shape. Well, the fundamental object in MATLAB is what we might call a higher dimensional array. It makes arrays. A matrix is an ordinary matrix that we normally refer to as a 2 by 2. A vector is a 1 by 2 or a 2 by 1. But it makes higher dimensional arrays. Let me explain what I mean by that. Say you've got a number of matrices, and the kth matrix we'll call MK. And I want to make a book of matrices. On each page of the book, I want to put MK. So what I want is then all the rows, all the columns, kth page to contain that matrix, which is specified in some way. It'll make then a book, which I'm calling M, such that on page K, so that says all the rows, all the columns, page K, we have this matrix. And you can do that and then do calculations on this whole book at once. So if you've got a whole lot of matrices, and you put all those matrices on pages of a book, and you want to do something to all of the elements in all of the matrices on all of the pages, you can do that in one command. So for example, I make these two matrices, and now I make a book. And on the first page of that book, I put M. On the second page of that book, I put N. So it makes this book. And if you now want to see what the book is, just type B. Then it tells you first page of the book, there's our matrix M. Second page of the book, there's the matrix N. MATLAB assumes that any variable that you make is one of these high-dimensional objects, and it'll adjust to your specifications. So for example, we've got a book now. So it's got rows and columns, that's a matrix. And now that book has got 2 pages, and now we want to make another book. We just make a new book from the old book by multiplying by 2. So I've got 2 books, B and 2B. And I put them on a shelf, shall we call it. Then this specifies that book B goes on the first position on the shelf, and 2B goes on the second position of the shelf. And if you want to have a look at the whole shelf here, then this is telling you in the first position then, on the shelf. That's what we call B. And there's the first page and the second page. There's the second position on the shelf, first page, second page. So just to go over that, that specifies the page, that's the book, and that's the shelf. So that's the book on position 1 of the shelf. This is the first page of that book. Well, here's a little exercise which you should really try right now if you're trying to seriously understand this. As with any mathematical field, the key understanding comes from doing exercises. So I won't talk too much, just page through these exercises, pausing each time, and try the exercises, and I'll put solutions up later on. So here's another one that you can try using a little for loop, and just keep paging through these exercises, pausing after each one. Here we go. Try this one, then this one, then this one. Here you got to use your knowledge of MATLAB to produce these matrices, and try and use MATLAB to do these computations, and just keep paging through these, pausing each time. Here's one which will help you to produce matrices using RepMat and things like that, and try this little exercise.